Hey, so today I'll be talking about the Beer-Lambert law and how we're going to use it to study the optical properties of beer. The basic idea of the Beer-Lambert law is that you have some material with a linear attenuation coefficient given by mu that describes how light transmits through your medium. And the way we describe this mathematically is through the transmittance being the radiant flux transmitted through the medium. So if you have a light source on the top, the transmittance is the ratio of the light that goes through over the light that is received by the medium, and that's over some distance h. And so you can describe this with a differential equation, d5t of h over ddh equals minus mu times the phi t of h. And so you can easily separate it and solve using initial value conditions. And it turns out that the phi t of 0 is in fact the case when h is 0, as you can see from the diagram. And so then you replace that, and then we find that the transmission is given by this law. And so this law is what we want to curve fit to based on data that we gather, and we want to find mu for different kinds of beer, meaning given a certain kind of beer, how do we describe how light propagates through?
This is the base of our apparatus. The phone goes inside this cavity here, and the camera faces upward, facing this hole where the liquid goes into. On top of the base, we have the liquid column. Here you see a plastic strip. This lets us see how high the liquid is in the chamber. This is so that we don't have to make volume versus height comparisons, and we can just do that using the apparatus. Finally, on top of the liquid holding column, we have the laser holder. The laser goes inside here, the tip first. The laser shines vertically through this column right onto the camera. A major design goal of this apparatus was to make it portable, in that you could easily assemble it, disassemble it. Field ecologists go out in the field and collect samples and take them back to the lab to analyze later. But using something like this, you could analyze right in the field, know if you have good or bad data, good or bad samples, and continue your work instead of finding out the hard way later.
Is that it?
Yeah.
The first thing to do when calibrating the instrument is to turn this dial so that it's pressing on the laser button, and you want it so that the laser is pointing on top of this red dot marked with the Sharpie. And the reason for this is because the laser is going to come down right on top of the camera, which is in my hand right now, and we can just use this Sharpie to mark where we already know where the laser hits it. Once this is done, the second part is to adjust the polarizer so that the light passes through the polarizer in a way that we minimize the amount of light coming through. If you can see there a little bit, you have a little bit of light left. This is because if you shine the laser directly onto the camera, it'll be too bright to notice differences in the intensity at different places. And there are a few joints here that we can use to adjust this if necessary. But for the purposes of this, you can just move it into place. So the way we want to determine mu is by replicating our setup from earlier, and so the medium that we're going to be using is going to be this empty, this hollow container which will have beer in it, and we know the height on it. And so we shine a laser as our light source through a polarizer to decrease the intensity of light so the camera can see it. And underneath we have a smartphone. And the smartphone will go in this under this small base with the camera phone facing up so that the laser is pointing right on the camera. And so when we do this, we can take a video and we take this plastic syringe and insert beer into the top so that we can vary H and get an idea of the transmittance at each H while taking a video. Hey, so once we have our frames in the right directories from the videos of their pictures of the light at each point of the height, we can give Mathematica a list of these heights in terms of centimeters, and what we've done is written a function so that if we give Mathematica a directory to look in and a list of all the heights and an initial guess for what mu is, then we can calculate all the parameters that we need. And so this is what the function looks like. And so it'll do some housekeeping stuff where it'll get the data in a form that makes sense, and then what it will do is fit the data to a model based off of the function that we derived from the differential equation. And so then we can plot this, and what we have is an error list plot, which shows us our data points with error bars on them, as well as the plot of the fitted model. And then from this we can get the residuals and the parameters that the model found, and then the associated errors, and then we output all these and give them back to the user. And so the result of this is that we get these nice plots with residuals on them, and in most cases we see pretty good results, and we'll talk more about these results in the discussion.
Okay, so just to recap this experiment, we're using Beer's law to measure the attenuation coefficients of beer using a 3D printed apparatus. Alright, so we 3D printed an apparatus that has a base for the phone, a middle chamber for the liquid, and a top cap that holds the laser. The laser shines directly into the camera of the phone, and we take a video and analyze it later. The method we used to implement the design when recording the video was to take measurements of the height on the side of the liquid cavity while pouring beer into the top so we can measure the transmittance as a function of height. Our method when implementing this was to take a video underneath, and while doing so we would record values of H, which were the height on the side of the apparatus. We were able to perform nonlinear fits and determine the attenuation coefficients, which turned out to be reasonable in what we would expect. In fact, we even found small errors. Okay, so we'd like to emphasize that our experimental setup did work and allowed us to test Beer's law. One interesting challenge that came up is when we were pouring the beer would naturally acquire a head obscuring the camera, so we had to devise a way to remove and mitigate that. That's something we didn't expect we'd have to do, and something we adapted to when the time came. In fact, in the future, this sort of apparatus could be used by really anyone who does work in any sort of field, any field work that has to collect samples. This apparatus could let you test and verify your sample immediately without having to go back to your lab, anything like that. And overall, I think it's a good experiment. Yeah. So, thanks.